Mixture of experts sounds mysterious until you build the router. The key idea is choosing which small expert should handle each input. This is the pattern you'll be able to implement by the end, which routes inputs to the best experts and mixes their outputs into final labels. I'm Professor Pi, teaching AI foundations with simple Python. Think of a real team of specialists. One person knows text about finance. One person knows medical terms. One person is good at short social sentences. A single big model tries to do all of that and gets expensive and slow. A mixture of experts instead keeps many small specialists and learns a router to pick who should speak. That reduces cost and can raise accuracy when each expert focuses on a narrower job. Intuitively, the router is a smart traffic director. For each input, it gives either a probability distribution over experts or it picks the most likely expert. The experts are simple functions that make predictions. Strengths include lower compute per query and clearer specialization. Weaknesses include extra coordination and possible instability if one expert dominates too quickly. We will build a small, clear pipeline in plain Python. First, a naive baseline that averages every expert. Next, a soft router that assigns probabilities. Then a hard router that picks one expert. After that, we tune how sharp the router is. Finally, we let two experts share responsibility. Keep this picture in mind before we drop into the first snippet. Now we start with a uniform baseline. This snippet computes a simple no-routing baseline by averaging the outputs of small expert functions for each input. The list experts holds 3 linear experts as slope and bias pairs, and excess contains 4 easy-to-read inputs. The function apply calculates an expert's output for one input using a times x plus b. The variable total sums every expert's contribution across all inputs using a compact generator expression. The final variable avg divides by the number of inputs and experts to get the overall mean prediction under uniform mixing. The printed number shows the average prediction if all experts are used equally, which grounds our intuition before adding any routing. Next, we add soft weights so experts get graded influence. This example routes inputs using softmax gating, so each expert gets a weight rather than equal averaging. The list GW stores simple router parameters as weight and bias pairs to form a linear logit for each expert given an input x. The list L holds those logits, and mathx builds a stable softmax in E by subtracting max L. The variable W normalizes those exponentials to probability-like weights. The final return multiplies each expert output by its weight and sums them, producing a routed mixture for one input. Averaging mix across XS yields an overall routed mean. The printed value shows how learned-like routing can shift predictions away from the uniform baseline. Now, we try hard assignment, where each input goes to one expert. This code switches to hard routing by selecting only the top one expert for each input. The GW list defines the same linear router parameters, and the function top1 returns the index of the expert with the highest logit for an input x. The list ins gathers the chosen expert index for every item in XS. The list counts tallies how often each expert index appears, providing a quick specialization snapshot. The variable M finds the most frequently selected expert. The printed index reveals which expert dominates routing decisions, making the ranking behavior visible and concrete. Next, we probe how sharply the router chooses by changing temperature. This snippet tunes routing sharpness using a softmax temperature and measures the effect. The function max weight computes the average of the largest expert weight per input across XS. Inside WTS, logits from GW are divided by tau before applying math.x, which makes the softmax sharper when tau is small and smoother when tau is large. The variable gap subtracts the average max weight at tau 2.0 from tau 0.5, showing how concentration changes. Lowering tau increases peaky assignments. Raising it spreads probability mass. The printed gap quantifies how strongly temperature shifts routing focus, a practical dial for stability versus specialization. Finally, we let two experts collaborate to see if error drops. This example shows a small but complete mixture of experts baseline by upgrading from top 1 to top 2 routing. The function topkmix rakes expert logits from GW for an input X, takes the best K indices, averages those experts' outputs, and returns the combined prediction. The expressions M1 and M2 compute mean squared error against a simple target function 1.0 times x plus 0.2 for k equal to 1 and 2. The variable imp reports the MSE reduction achieved by letting two experts collaborate. Allowing a second expert often captures complementary patterns. The printed improvement confirms that top 2 routing can materially reduce error on this toy task. To map this toy pipeline to a real system, imagine a search service with many short, specialized classifiers. Replace the toy linear experts with small neural modules. Replace the simple router with a lightweight learned gate. Use the same top K ideas to reduce latency while improving accuracy on diverse queries. Recap: a mixture of experts is a router plus many specialists that split the work. Use it when you want lower query cost or clearer model specialization. Caveat: routers can collapse to a single expert unless you tune sharpness or regularize. Next step: tune the temperature parameter across a validation set to balance stability and specialization, and measure both latency and accuracy as you change it. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.